review of power series. I think in this book, I think he just says power series. Um, and and then we will, at the end of this day, um, we will talk about how to actually solve a very simple differential equation using power series. As we go along in this chapter, the problems get to be a little bit more um, uh, difficult. But here in this section, we want to try to make the connection uh, back in Calculus 2 in Chapter 9 when you dealt with power series, Maclaurin, and the Taylor expansion. There was one little part in there, in that book, that hinted to taking a geometric series or a power series and you can integrate it or you can take the derivative of it. Um, and that whole process to be able to do that was in the attempt of here in this particular course to actually solve a differential equation using the power series. Um, so recall two important concepts from Calculus 2. One is the geometric series, and then the second is the ratio test. Um, our objective today, a couple things: to find the interval of convergence of a power series. That interval of convergence was something that we saw back in Calculus 2. I will go over it in detail right here. And then to be able to solve a differential equation by a power series representation. To do this, the student will reduce the functions, if possible, to a geometric series to relate the problem to something that you've seen before. And so our first review is on Part A, the geometric series. I do apologize for this blue small print here. It is difficult to see. I recognize that now. I think the expansion would, well, a little bit better. This is just the typical geometric series, how it was presented from the Calculus 2 book. What I want to pull out for you here is when we have a geometric series, some summation as n goes from 0 to infinity of a times r to the n, where r is a ratio. Hopefully it's between 0 and 1. Hopefully not necessarily 0, and then not necessarily 1 as well, but it's some ratio in between. If that be the case, then we said convergence. If r is greater than 1, then we said that the series would diverge. With this representation, we can take some function, any function, and represent it using a power series. And here, for example, the summation of x to the n, obviously as n goes from 0 to infinity, is set to based on the geometric series. Looking at this guy, the summation of a, here our a is 1, of some r to the n is equal to, if a is 1, you just get 1 over 1 minus x, if here x is equal to r. So basically we just took the geometric series from Calculus 2 and just rewrote it in a different fashion. It's the same thing. Example. So if that's the case, notice this. What if you have 1 over 1 plus x? So the question is, how can I write this function as a geometric series? No problem. This is the same thing as 1 over 1 minus a negative x. you recall the form for the geometric series has to be of this form here. That is that I have to have some constant, could be a, could be just 1, doesn't matter, over 1 minus something. And you can manipulate the minus. This is what we're doing here with this positive sign. So we write this as 1 minus a negative x. So if that be the case, this is the summation according to the geometric series as n goes from 0 to infinity. Here, this guy, 1 over 1 minus x, is said to be the summation of x to the n. So 1 over 1 minus a negative x is the summation of negative x to the n. Now the negative x is the same thing as negative 1 times x. So from there, raising that to the power of n is how we introduce the alternating series. So this is the summation. I tell you, these crazy computers. Wouldn't happen at the old chalkboard, right? Yeah, all this stuff popping up. Anyway, I hate this technology. But anyway, I'm this old grandson of a sharecropper in South Alabama. So this guy can be written as, this is negative 1. It's negative 1 times x, all raised to the n. So you can write this as negative 1 to the n times x to the n. Do you see that? So it's an alternating series. Watch this, another example. What if you have 1 over 1 minus x squared? You have the form. The form is at 1 over 1 minus x. That's the model that we go by. Is this guy here, 1 over 1 minus x, is equal to the summation of x to the n. So if that x is replaced with x squared, no problem. I'll write this as summation as n goes from 0 to infinity of here x squared to the n, and a power raised to a power, you multiply the power, so this is the summation as n goes from 0 to infinity of x to the 2n. So just that very simple note on the geometric series, and particularly if it converges, we can write the series, as a particular function. If it diverges, then there's something down here that I'm going to talk about, and so how we can classify convergence or divergence for a particular series, power series. So the second thing is to use the ratio test to find the so-called interval of convergence. And so primarily in this section, they will ask some questions where they'll give you a power series. They just ask, find the interval of convergence. It is identically the same to what you did back in Calculus 2. So basically this section, for the most part, 85% of it is just a copy of a section in Chapter 9 in Calculus 2. So let's see. Use the ratio test to find the interval of convergence. Well, here, I went to the calculus book and just copied this very same statement here for the ratio test. The ratio test was just said simply, given just a generic power series that is non-zero terms, the terms would be the a sub n. So the series is said to be convergent absolutely if the limit of the absolute value of the n plus 1 term divided by the nth term, if that guy is said to be less than 1. We have absolute convergence. If this ratio is greater than 1 or infinity, then we have a divergent series. And if this ratio is equal to 1, we don't know. We have to use something else. And back in Chapter 9, you get several other tests that you could use. Here, everything whereby the test that you will use here is the ratio test. So we talk about the question of convergence or divergence. Well, when do we get divergence? When do we get convergence? Everything is set to center around a so-called radius. So the idea here that if I have convergence, then there's an interval that is said to be satisfactory of the convergence. So within this particular neighborhood, we have convergence. Maybe going beyond that neighborhood, you may get divergence. That's a possibility. It may diverge everywhere. It may converge only at one point. It may converge everywhere. We don't know, but we tried to classify the convergence within three categories. So let R be the so-called radius of convergence, and we'll talk about that in just a minute. This variable 1 for the ratio test is manipulated by just some number that we'll call R. And we can use that number. Obviously, if this number here, 1, if it's 5 and you want to get 1, so the ratio is less than 1, just divide everything by 5, right? And you get the 1 again, so it's no problem. It is, sometimes you can look at the series and determine what R will be. Most times you probably won't be able to, but we can do some work. We can do some work to it. And the work that you're going to do to it is applying the ratio test, and it'll give you exactly what you want. So consider a power series in its general form, summation of as n goes from 0 to infinity. I do apologize for that. Of some c sub n, these are the terms. If you remember back in Calculus 2 when you were having to use the Taylor series or the Maclaurin, you had to find all those constants, C1, C2, C3, whatever, and you take the derivative, first derivative, second derivative. Well, the good thing is you won't have to take all those derivatives here. This is confined to just nothing but algebra and arithmetic. Maybe 1 or 2 derivatives, but very straightforward. Of some x minus a is just said to be the number that pulls x. We call a the center. X minus a, that's to the nth power there. Let me pull this screen up a little bit so you can see what's happening down below. So what we're saying is that if you give me this series here that we have in blue, then if I look at x minus a in terms of the absolute value of x minus a, it's said to be less than some number r. Let me write that. Where r is this radius of convergence. What that gives us is that negative r is less than x minus a is less than r. If I solve for x, then I have here negative r plus a is less than x, and that's less than r plus a. So a being the center here, right? And so the area to the right of that would be the r plus a or the a plus r. It's this guy right here. And then the area to the left of a would be the negative r plus a or the a minus r. So everything confined within that interval here, we're said to have absolute convergence. Anything beyond that is said to be a divergent series. Now, here are the 3 possibilities that I've classified down below. And as I state each one, I can talk about the dichotomy as well. If r is equal to 0, that means that on the interval, that I only have one point where I have convergence. So it doesn't go anywhere. So here, if r is 0, then at x equal to a, I have convergence at that point only. Everywhere else, here's a dichotomy, everywhere else it diverges. So here, if r is equal to 0, the series converges only at that point, right? So then obviously everywhere else, you don't get convergence. Number 2, it's possible that the radius is the entire interval. So you get convergence everywhere. I don't have to go looking for that. As I manipulate all 3 of these cases, we manipulate the ratio test. That's the only thing I'm doing. 2 things that I'm introducing is all I use. I give it to you. The geometric series and the ratio test. That's all you need to know. The series converges absolutely, just going back to what I just wrote up here, if the absolute value of x minus a is less than r. If we have the absolute value of x minus a greater than r, then we have divergence. So number 3 is the dichotomy. Either you have convergence or divergence based on what's happening with this measurement from x to a. Again, the problems will, if I let it do what it's supposed to do, I'm going to see obviously what's going to happen. Remark: when finding the interval of convergence, you want to check the endpoints. Something similar that we did back in calculus 2 as well. And I'm going to do all this right now. Just some problems from the book. Find the interval and radius of convergence for the given power series. Let's take number 1. So this is the summation as n goes from 1 to infinity of negative 1 to the n over n times x to the n. So the first thing we do is apply the ratio test. So the ratio test is the limit as n goes to infinity of the absolute value. Now, if you don't mind, I know a lot of these problems will have like negative 1 to the n for that alternating series, but since I'm taking the absolute value, that's going to go away anyway, so I'm not going to even write it. Right? So you don't have to write the negative 1 to the n when I'm dealing with the absolute value. So I'm just going to write everything else that I have. If you put that in there, it's okay. It's still going to go out once you look at the absolute value of it. So I'm going to write the other terms. So the top for the ratio test is the n plus 1 terms. This is x to the n plus 1 over n plus 1, and this is divided by the nth term, x to the n all over n. Just simplify that. This is the limit as n goes to infinity of the absolute value. This is x to the n times x, right? X to the n plus 1 is x to the n times x over n plus 1. It's divided by, we convert the division to multiplication, flip the second fraction. This is times n over x to the n. Now we see what cancels out. The x to the n cancels out. Now for the ratio test, you recall, for the ratio test to be convergent, this whole limit has to be less than 1. So let's see what we have here. This is the limit as n goes to infinity of the absolute value of x times n all over n plus 1. So we're trying to get convergence. Let's see. For the ratio test to be convergent, this guy has to be less than 1. I can always manipulate that based on the selection of x. Why do I say that? Here's why I say this. If you look at this limit does not restrict x. The restriction is on n, right? It's the limit as n goes to infinity. It has nothing to do with x. X is going to be some number that the user for the computer program that they supply. So if that be the case, but it does say this, and we have to be consistent. Whatever is confined to the absolute value has to say absolute value. So what I do is we say this implies, just simplifying this is the absolute value of x times the limit. I can take that x out, but it's still the absolute value. Now here, n is going over positive terms, and n over n plus 1 is still positive, so this is the limit of n over n plus 1. We want this to be less than 1. How is that possible? Well, what's the limit of n over n plus 1? The limit of 1 over n plus 1 is 0. The limit of 1 over n is 0, right? The limit of n divided by n squared is 0. The limit of n divided by n to the 5th is 0, right? But the limit of n over n plus 1 is 1. Where did you get negative from? Oh, boy. Too much Easter dinner, right? Easter dinner was really good, right? Man, I really pigged out, man. I messed up. Brought some today, too. Anyway, this limit here, when you're looking for the limit, do you remember in algebra where we did the vertical isotope and the horizontal isotope? If you remember how to find the horizontal isotope, that's the limit of the function. It's the same thing. So for the horizontal isotope, you recall that we said to find it, it's set to be the ratio of the leading coefficients, a sub n divided by b sub n. And we said that you had, let me move that cursor, you had, 2 or 3 possibilities for that. That if the power of the numerator is the same as the power of the denominator, then the horizontal isotope is the ratio of their coefficients, 1 divided by 1, which is just 1, right? And the horizontal isotope said that if the power of the numerator is less than the power of the denominator, then the horizontal isotope is equal to 0, which is the same thing as a limit. If the power of the numerator is bigger than the power of the denominator, then the horizontal isotope was infinity. They were talking about the limit. So this part here, its limit is 1. So what I have is the absolute value of x times 1 is being forced to be less than 1. I can do that. So that is the absolute value of x times 1 less than 1. So this is negative 1 less than x less than 1. You recall that the absolute value of x minus a less than r, where r is the radius. Convergence. The first question is what's the radius? The radius here is 1, right? It's of this form here. So here r is equal to 1. And now we want to find the interval of convergence. This is not altogether the interval of convergence because you have to check the endpoints to see what happens at x equal to negative 1. What happens at x equal to 1? Is the series convergent at x equal to negative 1? I don't know. You have to check. Is the series convergent at x equal to 1? I don't know. You have to check. So check the endpoints. So here at x equal to negative 1 and at x equal to 1. Now when you check the endpoints, that's where you have to kind of go back and dig up some of those tests from calculus 2. Let's see. So here at x equal to negative 1, I go back to the series. I'm going to replace x with negative 1. So this is the summation as n goes from 1 to infinity. This is negative 1 to the n. This is times negative 1 to the n all over n. What is negative 1 to the n times negative 1 to the n? Which is what? Oh, it's just 1. Negative 1 to the n times negative 1 to the n. I mean, you can complicate this, folks. Here's the complicated version. Negative 1 to the n times negative 1 to the n is negative 1 to the n plus n, which is negative 1 to the 2n, right? So negative 1 to the 2n is negative 1 to the 2 raised to the n, right? So negative 1 to the second is what? 1. 1 raised to the n is what? 1, right? Just negative 1 to the n times negative 1 to the n is equal to 1. That's the easy way. Right? Negative times negative is positive, man. Keep on moving. Keep on pushing. Okay. So this is the summation as n goes from 1 to infinity. Of just 1 over n. Is this convergent or divergent, and why? This is our favorite part in calculus 2, right? No, you hated that. But anyway. Did you like that section, Friaja? You remember that stuff? All those series tests? So, the summation of 1 over n. Convergent, divergent, and why? What tells us? You're thinking about a sequence. This is a series. Totally different. All right? The limit of 1 over n is equal to 0. Right? That converges. But the series, you're adding up all those terms here. So they're not going away. Right? Oh, it's going to be a long summer. The summation of 1 over n, it was one of our most simplest series. It was called a harmonic series. Harmonic motions, where you get that from? Back even connect that with chapter 5, section 1. It's the same thing that's happening. Matter of fact, you can prove that this is equivalent to the sine omega t plus cosine omega t. This was harmonic, we said, but it's what? Is it convergent or divergent? Remember the P series? The P series says summation of 1 over n to the P, that it diverges when P is equal to 1, but it converges when P is greater than 1. All right. This P series divergent. All right, now we check at x equal to 1. So I replace here x equal to 1. So we replace the x to the n with 1 to the n. So we have the summation as n goes from 1 to infinity. Negative 1 to the n times times 1 to the n all over n. This is the summation as, well, 1 to the n is just 1. So this is negative 1 to the n divided by n. This is convergent or divergent, and why? Is it alternating series? How do we know if it's alternating series? It's negative 1 to the n, right? It means that the values are going to alternate. Negative, positive, right? Negative, positive. Right? So yes, it's alternating series. And if it's alternating series, is it convergent or divergent? But how do you tell if alternating series is convergent or divergent? Remember the test was two cases there. For the alternating series, once you see that it has negative 1 to the n, you take the limit of the sequence. Take the limit of 1 over n. It said there that for the alternating series, that 1, if the limit is equal to 0 for the sequence, and if those terms are decreasing. Well, they are. Right? You start with 1, you get 1 over 1. You get 1 over 2, 1 over 3. They're getting smaller and smaller. Well, the actual theory says that it has to be, it has to be changing in the sense that they're increasingly getting small. It could say that they're increasingly getting larger, but if they're increasingly getting larger, then the first part for the limit would not equal to 0. So here they say limit has to be equal to 0, and that the terms must be decreasing. Well, that is the case. So this is alternating series convergent. So at x equal negative 1, it diverges. At x equal to 1, it converges. Everything in between worked out. So we conclude here the interval convergence is open at negative 1, comma, closed at 1. Let me do one more, and then I want to try to work a problem where we have to solve the power series. So just do one more here. Is everybody with me? You have to do some recalling, right? You have to go back and recall some of that stuff from Calculus 2. And probably between Calculus 2 and now has been a whole lot of other stuff that you've been kind of running up against. So. Let's see what's different. I guess the number 4 is different. And so let's look at number 4. Number 4. So n goes from 1 to infinity of 1 over n squared. Oh, this is a good one. No, that's number 2. Sorry. Yeah, number 4 is okay. So the summation as n goes from 0 to infinity, 5 to the n over n factorial times x to the n. So we apply the ratio test. the limit as n goes to infinity of the absolute value of the 5 to the n plus 1 times x to the n plus 1. This is over n plus 1 factorial divided by the nth term, 5 to the n times x to the n all over n factorial. So this is equal to the limit as n goes to infinity of the absolute value. You can write the 5 to the n plus 1 as 5 to the n times 5. And then the x to the n plus 1 is x to the n times x. This is divided by, that n plus 1 factorial can be written as n plus 1 times n factorial. Well, I better leave it as that for right now. And this is times n factorial all over 5 to the n times x to the n. Now the 5 to the n cancels out, and the x to the n cancels out. So I have left. Something else is going to cancel out with that factorial. I just didn't simplify the n plus 1 factorial. So this is the limit as n goes to infinity of the absolute value. Here this is x times n factorial all over the n plus 1 factorial. You think about it. If you have 6 factorial, can't you write 6 factorial as, well, obviously it's 6 times 5 times 4 times 3 times 2 times 1, which is the same thing as 6 times 5 factorial, right? So you can write n plus 1 factorial as n plus 1 times n factorial. N plus 1 times n factorial. Yeah, that 5 should be up there, right? I forgot to put it there. Yep, that 5 there. And what, yeah, we got the x. I just forgot the 5. Thank you. So the n factorials cancel out. So let's write this now. This is the limit as n goes to infinity of the absolute value of 5x all over n plus 1. Excuse me. Look at this. This is the absolute value of 5x. I'm going to pull that out. It has no bearing on the n plus 1 term. N is going to infinity. This is times the limit as n goes to infinity. Since 1 over n plus 1 is positive, just write that as 1 over n plus 1. What's the limit of 1 over n plus 1? 0. That's less than 1, right? For the ratio test to be convergent, right? It's less than 1. Whenever you get this limit here for the ratio test to equal to 0, this actually means that, watch, for any selection of x, you're going to always get convergence. Right? Because basically you're saying, 5 times x times whatever x is, right? Times 0. X can be any term. But here, the limit going to 0 just forces for us any selection of x. I'm going to always be guaranteed absolute convergence. Here my interval of convergence is the entire number line. It doesn't matter what choice of x you make. So like any x value on the number line, I'm going to get that x value times 5 times the limit of 1 over n plus 1, which is always 0. Converges everywhere. Right? So here, since this limit is for any choice of x, whereby we still get convergence. So since the limit is for any choice of x whereby we still get convergence, here the radius of convergence is infinity. And the interval of convergence is from negative infinity to positive infinity. That limit going out to be 0 helps us get there. Right? Can you check the endpoints here? That was the next thing. The first thing is you apply the ratio test. Then after that, you check the endpoints. We're going to check the endpoints on this one. No. It'll take you a very long time, right? Because the endpoints are infinity, right? You got to be able to go out there and get it first to be able to check it. So it's too far for me. Steps to solving a differential equation using power series. Tell you what, I've got a couple of minutes. I won't go there. I'll save that for tomorrow. Let me back up. Now number 5 is good, but why don't you do number 2? Find the interval and the radius of convergence. We have about 8 minutes there. Bless you. So that's the summation as n goes from 1 to infinity of 1 over n squared times x to the n. Work number 2.